guys, I'm back. This is the next part of Unit 15, and we have a real short little video today over reaction mechanisms. Now, we so far have studied reactions that just occur, basically. We have the reactants, we have the products. In reality, most reactions actually occur in a series of steps where you have a reactant that you start with, or group of reactants, and they go through several reactions until you finally get to the products. We have been writing the very simple form of that so far, but in reaction mechanisms you are showing all of those steps. Now, one thing to know is that a reaction is only as fast as its slowest step. And so this is called the rate determining step. And when you write reaction mechanisms, they are written as steps. And you have simple reactions that are related to each other by the products becoming the reactants in the next reaction. And it's kind of carries on over. And in reaction mechanisms, each step is always labeled with a fast or a slow. It's usually very simple, straightforward like that. They don't give you a time. They don't tell you how many nanoseconds it takes or whatever it is. It's just fast or slow. And so the rate determining step will always be that slow step. Also, in reaction mechanisms, there are two things that I want you to be aware of. First of all, in some of these, there will be a catalyst. And we've talked about catalysts before, and they are substances that are put into a reaction in order to speed it up. They're the detour. They do not become part of the final product, just as they are not listed as part of the initial reactants. So usually when we write reactions that have a catalyst, we would put something over the arrow. In reaction mechanisms, you will always see a catalyst being used in the very first step as one of the reactants. In this equation, I have it written as A. It could be anything. It would be an actual chemical. Here I have it used as A, or listed as A. And notice that I start with it in the first step, and that in this case I end with it in the second step. Now, some reaction mechanisms are very short, like this one, just 2 steps. Some could have 3 or 4 or 10 kind of intermediate steps. In each one of those, if there is a catalyst used, the catalyst will be a reactant in the first reaction and a product in the last reaction. And so that's what A is representing. Another thing that you won't see kind of in the finalized form are what are called intermediates. Intermediates are compounds that are formed in one of the beginning steps, and then they are used up at the end. I have OA listed as my intermediate. In this case, again, it could be any compound or element, but notice that it is a product first, and then it becomes a reactant. And so it is made and then is used. And so with these steps, you can kind of cross out the things that get used up or that you don't see in the final reactant, and then you can basically add up all of your steps to find the actual reaction. So in this case, that the 2 things that I've just talked about, the catalyst and the intermediates, don't end up in this final reaction. So here's our final reaction. They don't end up in there because in reaction mechanisms, anything that is on opposite sides of the arrow, as long as they are the same exact thing, basically cancel out. Same thing for the intermediates, that would cancel out if they are opposite of each other. And so then after you've crossed everything out that you don't need, you simply add. And so my N2Os and my N2Os will add, and I have 2 of those, and then nothing else. That is my reactant. And then they form my N2 and N2, so I have 2 of those, plus that O2. And that would be the overall reaction for this reaction mechanism. With these, again, I have a very simple one here. We'll deal with mostly simple ones. They can be very complex, and it's kind of like putting a little puzzle together to kind of get everything added and figured up. But I want you to just kind of see what they are. Now, here's the same one again. Again, sorry if you rewrote it. Oftentimes with these reaction mechanisms, you will be asked about a graph. We've talked about the graphs before with the activation energy and the, going from the reactants to the products and the time basically that it would take. If you have a reaction mechanism, for each step that you have, you will basically have a hill that you have to get up. And so because each one has to proceed. And so with the reaction mechanism, sometimes you'll have to identify a graph that would match up with that, with those steps. So for our example, in step 1, you're told that it is slow. You'll always be given that information. And that step 2 is fast. And so looking at these two graphs, remember how the hills work. Remember that if you have a tall hill, like you do in this first reaction versus this little small hill, this is going to take a longer time. So here you have a slow or a longer time versus a fast. And then on the other one, you have a little hill to go up first. That's going to be pretty fast. And then a much bigger hill, which would take you longer. So that one would be slow. So based on the order of our fast and slows, the graph that best represents our example reaction, so the slow fast, is going to be this one, okay, because it matches the times. All right, hey, that's kind of nice and easy. Let me know if you have questions on this. We will continue on next week with more of the reaction rates. Let me know if you have questions. Thanks, guys.